All right, we're going to continue our conversation about compound operators. And in this video, we'll be speaking about the conditionals and biconditionals. Definition 2.23. The conditional statement. Involving P and Q, and it's denoted by this P arrow Q. So that's the arrow there. I'll make that better. So that's its symbol. Is the proposition if P, then Q. And by definition, it is false when P is true and Q is false. Okay, so let's really break that down. We have if P, then Q. Q is often called the, P is often called the premise or the hypothesis. And Q is often called the conclusion or the consequence. And I like the terms hypothesis and conclusion, but books and lectures may differ. So let's break this down further. Let's really kind of make a table here of what's happening. So first off, we know, let's just go by it's false, because this is the only time it's false. So it's false when we have a hypothesis that's true and a conclusion that's false. And all the other times it's true. So it's true when, this is probably the most natural way to think of it's true, is if the hypothesis is true. And if the hypothesis is true and the conclusion are true, then the conditional statement if P then Q is true. And that's natural to think. So if I say if I'm hungry, then I eat, and if both those are true, saying I'm hungry is true and I eat is true, then the conditional makes sense. If P then Q. If I'm hungry, then I eat. What's really counterintuitive are the other true statements. So it's also true if we have a hypothesis that's false. And it doesn't matter at all, actually, what the conclusion is. So the conclusion could be false as well. And overall, though, the conditional is true. And we also have, again, like I said, it doesn't matter if the hypothesis is false, all bets are off. It doesn't even matter if the conclusion is true. We'll say that the overall statement, the conditional statement here, when I mean the overall statement, I'm referring to these conditionals. Those are true. And that's pretty counterintuitive. I don't want to get too hung up on it. So always I just really fall back on the definition here. It's false when I have a hypothesis that's true and a conclusion that's false, which makes sense because you're kind of like breaking some sort of deal. This one also makes sense, but these ones I honestly don't love trying to wrap my head around. But we'll try our best in an example here. So let's do it. So I'm going to follow the book's example, just so if you're reading the book, maybe it gives you a better understanding, or if it didn't give you understanding of the book, maybe the video will here. So P is you earn at least 94% on an exam, and Q, you will receive an A. Okay, well, let's do then if P then Q. What does that say? That says if you earn at least 94%, then you will receive an A. Let's also look at if Q then P. And that's if you receive an A, then you earned at least 94%. Now on face value, they sound very similar. And in regular English, we confuse this all the time, but in the language of logic, we have to be a little bit careful. The if P then Q, if Q then P are not logically equivalent. So I'm going to try to walk you through a scenario. Consider the scenario. So where P is false. That really means that you earned less than 94%. And let's consider the scenario where Q is true. That is, you received an A. Okay. By definition then of implication, we have if P then Q, the overall statement is true. And then the overall statement of if Q then P, that is false. And again, P here, we're considering this scenario where P is false. And remember, in this implication world, if the hypothesis is false, all bets are off and the implication just becomes true overall. So it doesn't really matter that Q is true. And here we have Q is true and P is false. And that's where you've broken the promise, so to speak. You promised if something, then something else. Well, you completed the if something, but then the back end of that promise was false. So then the overall statement implication is false. Again, like I said, I don't love the trying to interpret the implication or the conditional. If the book says so itself, if you read that section there, this is an example to go off of. And just at this point, if it doesn't really click with you, just fall back on the definition like I did there. And right now at this point, you should try reading exercise 2.26. So pause the video and try reading exercise 2.26. All right, and the last operator that we're going to learn in this section is the biconditional. Definition 2.28. The biconditional statement involving P and Q. And that's denoted by P if and only if Q, so kind of a double arrow there. is the proposition P if and only if Q. Sometimes it's abbreviated P if and only if Q, double FQ. And this is actually, we don't explicitly say this in English, but a lot of times this is what we're implicitly meaning in our everyday speak. So a lot of times if I say, if I'm hungry, then I'll eat, somehow we'll confuse that and say, okay, well, if I'm eating, then I also must be hungry, which isn't actually really the case. But in other words, this biconditional is the one that will often confuse with the conditional. And in logic, we want to be a little bit more precise. So it is true when I say it, I'm talking about the overall biconditional implication. It is true when P and Q have the same truth value. And false otherwise. Okay, so let's walk through an example again, and this actually is the reading exercise out of the book. So P if and only if Q, we're going to assume this is true, that the overall biconditional statement is true, and we're going to go off those examples from last one, which is P is you earned at least a 94%. And Q is you earned an A, or you receive an A. Okay, so if and only if Q is true, if we're assuming that the biconditional is true, then that really means that P and Q, this implies that P and Q have the same truth value. Okay, so we have that, and then I think it's example A, we're saying, if you earned at least 94%, are you guaranteed to have also received an A? Yes, because we're saying if P is true, if you earned at least 94%, then Q is true. Because again, we're assuming that the biconditional is true, which implies that P and Q have the same truth value by definition. Because it says right here, this biconditional is true when P and Q have the same truth value. Okay, so yes, if you do earn at least 94% in this situation, you also will guarantee to receive an A. Okay, and then B is saying if Q is true, on the other hand, if you received an A, is it necessarily true that P is true? And that's, again, for the same reasoning, it is. So in this case, if you received an A, then yes, you also earned at least 94% because, again, we're assuming that the biconditional is true. We're assuming this is true, which really implies that P and Q have the same truth value. So if Q is true, then P also must be true. They have to have the same truth value. And then C is saying, in the example from the book, if P is false, in other words, you earned less than 94%, is it necessarily true that you don't get an A? Does that imply you don't get an A. And yes, that is also true. Because again, back to the definition of the biconditional, if it's true, the biconditional, P if and only if Q, then P and Q have the same truth value, those stuff in the red. And so if P is false in this situation, Q also must be false. And so if and only if Q is a pretty strong statement, it's saying if P is true, Q is true, and if Q is true, P is true, and then the opposites, really, the negations. If P is false, Q is false. If Q is false, P is false. So they're almost equivalent in one way of thinking about that. And when we get to a proof section, we'll talk about that as well. And that ends our section on the logical operators. Again, in review of this particular video, we talked about the conditional, if P then Q, and we talked about the biconditional, P if and only if Q. And then previous logical operators we talked about were the negation, the conjunction, which is really and, the disjunction, which is really the inclusive or, and the exclusive or. So we learned about those for logical operators as well. All right, see you in the next video.